Okay guys, let's take a look at today's lesson. It's on Euler's method. So let's move this over out of the way. What I would like to do is talk about Euler's method and at the same time remind you what linear approximation is, because we still have a little bit of issues with linear approximation. Recall that linear approximation is the tangent line. You use the tangent line to approximate the function. So on linear approximation, we would, probably have this value. We'd write the tangent line, and we'd use the tangent line to approximate values on the function. I mean, that's what linear approximation does. This technique is different than linear approximation in that it doesn't just use one tangent line to approximate points on the entire graph. It does use the derivative, so let's kind of walk through that. So we do have to have a derivative. I want you to note that they're equating, and this is typical for most calculus textbooks. They say y prime equals f, but then when students look at the equation, it's kind of confusing because we're not used to thinking of f as the derivative. But it is, that they're saying y prime is f. Okay, so that's the derivative. We have to be given the derivative, and we have to be given an initial condition. Okay, so those are the two things that we need in order to use Euler's method. So the purpose of Euler's method is another way to approximate a function. So if you recall, Friday we learned how to do slope fields, and slope fields approximates the solution graphically. We could look kind of what would the solution look like graphically. Today's technique is approximating the differential equation and basically approximating the actual values. It's a numerical estimation technique. We're using values, numerical values, to approximate what the function would look like, the solution would look like. So that's the difference between, Friday's estimation technique and today's. Friday was graphing, today is numeric. So what do? Step 1, we choose a non-number 0, delta x, to serve as an increment or step size. Now, we're really not going to be able to, they're not going to let us choose what the step size is. They'll either tell us or they'll give us such restrictions that there's only one right answer. There's only one right answer for the step. So we do have to have the step size, and we find here, this little formula says that we take our our x naught, that's our initial x value. To get our x first y value, we take our x naught and we add delta x. Now that's kind of a complicated formula, but I think it's pretty common sense. If that's the change, the step size, we're just going to add that over and over again, right? We're going to take our original x and we're going to add the step size to our original x, and then the new x, and then the new one. But I'm going to work through that formula with you on the next slide, just so we have a good overview of what's going on. Where we get to the meat of it, or the what some students find is the complex part of it, is this portion right here. It's an iterative process, so I can really do this like as many times as I want. I can continue to calculate the next. If you look here at this diagram, we start with the very first, this is the given initial condition. And we use this formula to calculate the next x1, y1. So this would be the next location. Then we use x1, y1 to calculate x2, y2. And so basically what we're doing is we're using the previous point to calculate the next point. That's how this process works. The previous point to calculate the next point. And we could just keep going on. And what it does, in this particular situation, it creates a similar curve to the original curve. Though we're really just looking at numerically, what are the values? Okay, so if I made my step size smaller, what do you think would be the result? The smaller the step size, the more accurate, right? The more accurate my approximation is going to be. All right, so here's the first iteration. So for y1, or for this next point right here, what we would do is we use the previous point. That's the thing to kind of keep in your mind. We use the previous point every single time. So the previous point to y1 would be, you know, x naught, y naught. That's the previous point. That's the point that we're going to use in our formula. So I use my previous y value. I put my previous x and y value in the derivative. This is the portion that is the derivative. I'm going to plug in my previous x and y value in my derivative, and then I'm going to multiply that number by the step, or delta x. That's the procedure that you do over and over and over again. Okay, so for the next one, y2, what would I do? Well, I would take the point that I found here, my y1 and my x1, and I would use that in this next formula. I don't go back to the original, I just use the one previous. So the point that I got previous was this one, x1, y1. I would use this, and then I continue as many times as I have to. Okay, and I'm going to do a few examples of this. If this is like, what is she talking about? It makes no sense. I'm just going to do a few examples, and hopefully that will make sense what was going on. So the numbers y1, y2, and y3 in these equations are the approximations of, you know, the function at x1, the function at x2, and the function at x3. I mean, that's what you're finding. You'd be finding these. Well, these are approximations, the function at x1, the function at x2, function at x3, so forth. Okay, that's what you're doing. All right, we also are going to look at accuracy of Euler's method. We're going to look at absolute error versus percentage error. So if the question asks for error, it just says error, it means this one, absolute error. Okay, it may not use the word absolute. I'm just kind of letting you know, it may not use that word, but that's what it's asking for, that's the error, is the absolute value of the exact minus the approximation. Or it may ask you for percentage error, and the percentage error formula is exact value minus approximation over exact times 100, so that puts it in percent. Okay, and we'll look at those. Questions on this first slide so far before we go to the examples? Okay, let's flip over to the next slide and look at our examples. All right, our first example says, given the differential equation, so here's our derivative right here. You might want to highlight it, do something, pay attention to it. That's usually, for some reason, the portion of this formula that students have the greatest difficulty with is the differential equation part. So do something, highlight it or something. So let y equals f of x be the particular solution to the given differential equation with initial condition. Okay, so this is important also. This is our initial condition. So our x naught is going to be 4, and our y naught is going to be -1. That's what we get from our initial condition. Use Euler's method starting at x equals 4 with 2 steps of equal size to approximate f of 4.2. Okay, they don't tell us what the step size is, but they make it so restrictive as to there's only one right answer, right? We're going to have to start with what we know. We have to start at 4. A lot of times they don't even say where to start. This is like extra information that we usually don't have. We're going to start at the initial condition. That's where we're always going to start. So we're going to start at 4, and we need to get to 4.2, and we're required to use 2 steps of equal size. Okay, that's pretty restrictive, right? There's only one right answer to what our delta x is going to be, and it's 0.1. And that's the only way to do 2 steps of equal size to get from 4 to 4.2. So our delta x is going to be 0.1. Okay, now for this first problem, I'm going to write through how that formula on the previous page, how to find x1 and x2. I think that once you see it, you'll see it. That's really obvious. We know how to do that. We don't need to use the formula, but I'm just going to show you how the formula works. So it said x1 equals x naught was 4 plus the delta x was 0.1. So my x1 would be 4.1. Okay. My x2, we always use the information in the previous equation. My x2 is 4.1 is my previous x plus 0.1 equals 4.2. And I think that's kind of common sense, right? We understand where that comes from. I don't think we need a formula for that. So that's how we generate the x values. So now let's use the other formula, the formula that generates the approximations. So let's start with, and I really, instead of using y1, y2, that's so abstract, it really helps me in this process if I use like function notation, like either y of, 4.1 or whatever the function is. This doesn't really, it's f, so this name is f. So we're going to use, what I'm going to do is I'm going to do f of 4.1. In the formula on the previous page, this was y1. Okay, but I don't like that notation because it's not as specific enough for me. I want to know, be able to look at the previous equation and see what numbers I'm supposed to use. So f of 4.1 equals. Now keep in mind, on our very first iteration, we use the original x and y values. That's what we do. So the formula says take the previous y value, which in this case is -1, add to that the derivative. Now I'm going to put a big space here. I'm going to go back to that in a moment because that's, again, the part I think I need to focus on a little bit more. So I'm going to put the derivative values here, and then I'm going to multiply it by my step, which is 0.1. So let's see, how do we get this? Where does this come from? What we do is we go back to our differential equation, and we sub in that previous point, whatever it was. The previous point happens to be 4, -1. So I'm going to put in the x value of 4 plus the y value of -1. Okay, that's what goes there. It's basically, this is going to change every time depending on what your derivative looks like. Every time, right? This is going to be different depending on the derivative. This is going to be the same. This is going to be the same. This is what is going to change from problem to problem. From problem to problem, it's going to look different. It's not going to always be x plus y, because it's x plus y because that's what this derivative is. Okay? So we use our calculator. This is a calculator lesson. We put these numbers in our calculator. We get -0.7. Okay, so for the next iteration, so now we're going to, it would be y2 if we were using the formula on the previous page. I'm going to call it f of 4.2 because I think that is more helpful to me. So what am I going to do? I'm going to use the x and the y value from the previous equation. Okay, that's why it helps me to put this x value here. Otherwise, I'd have to figure out what it was. I think, what is the x value from the previous equation? All right, so let's just clean that up a little bit. So I'm going to take the y value from the previous equation. The y value from the previous equation is actually this, -0.7 plus. Okay, we're going to plug into the derivative. I'm going to leave that blank for just a moment, and then I multiply by the step. Okay, so now let's worry about plugging into the derivative. Now the derivative we saw above is x plus y. I need to use the previous x, which is 4.1, plus the previous y, which is -0.7. Okay, now I use my calculator. I put that in my calculator, I get -0.36. So that means that f of 4.2 is approximately -0.36 using Euler's method with the criteria they gave us. Okay, how's our very first Euler's method? That's my step size. Because I have to start at an x of 4 and I have to go to 4.2, and I was supposed to use 2 steps of equal size to get there. So that's my only choice. Other questions? Okay. All right, well, let's look at our second example. So we want to use Euler's method with a step size of, now this time they tell us the step size. Sometimes they do, sometimes they, make it such that we have to figure it out. But again, there's only one right answer. Step size is 0.2 to estimate the value of y of 0.4, where y is the solution of the initial value problem. So here's my derivative. Okay, that would be dy dx equals y. That's my derivative. Okay, I'm going to need that for my formula. And here's my initial condition. So x naught is 0 and y naught is 1. Okay, those two things you have to use Euler's method. Okay, the next sentence has to do with error, so let's hold on that till we get to that part. Let's figure it out first. So we're using a step size of 0.2, so delta x equals 0.2. And we have to start at 0. We have to start with what we have, right? We don't get to pick. So we're going to start with an x of 0, and we're going to go to an x of 0.4. And our step size is 0.2. Doesn't tell us how many steps to do, but there's going to be 2, right? If you're going to go from 0 to 0.4 and your step size is 0.2, that's what's going to happen. So let me get us a little room right here. All right, so let's start our first iteration. I'm not going to do this formula right here. I hope that we're okay. We know that we are starting at 0. So x naught is 0. So x1 would be 0.2 because I'm using my step size of 0.2. And then x2 is 0.4. You don't have to write that. I'm just writing that just to make sure we're perfectly clear on where that comes from. All right, so let's start our iteration. So they're using the y of, so we'll do y of 0.2 equals. This would be like our y1. We take the original y value, which is 1, plus, we're going to put the derivative value in there, times the step. And that's what the formula is, or the y value plus the derivative times the step. So the derivative, let's see, the derivative actually just has a y in it. So I take my original y value, which is 1, and that's all we have in this one. We calculate it, use our calculator, and we get 1.2. Okay, we okay? So I take my next iteration, so y of 0.4 equals, I'm going to take the previous y value, which is this one that I calculated, which is 1.2 plus, leave a space for the derivative value, which I'll calculate in just a moment, times the step. Okay, let's go back and work on the derivative value. The derivative just has a y value, so I'm going to use the previous y value, which was 1.2. I put that in my calculator and I get 1.44. So that means that y of 0.4 is approximately 1.44. Now let's pay attention and look at the second sentence, what they're wanting us to do. If the exact solution of the initial value problem is y equals e to the x, find the error made in using Euler's to estimate. Okay, so if the exact is y equals e to the x, if I want to find the exact value of the function at 0.4, I would say y equals e to the 0.4, and I'd put it in my calculator, right? I'd put it in for x. So I put that in my calculator, and I get 1.49182. So that is my actual value of that differential equation. All right, so now let's calculate the error. It just wants error, so that means the first equation, where we just do the absolute value of the exact, which is 1.49182, minus the approximation, which is 1.44. So our error is going to turn out to be 0.05182. That's our error. And that's our approximation. Okay, how are we on that? Is everybody okay?